Golden Iris Productions presents Einstein's Special Relativity and Reality, When Intuition Meets the Speed of Light, by Mark F. Dennis. Einstein's two postulates for special relativity. First, the laws of physics are identical in all inertial frames of reference. The speed of light is constant for all observers. Everything that follows is a consequence of these two postulates. Simultaneity. We begin with something that seems unquestionable, the idea that there is a single shared present. Right now, this moment feels universal. It feels like something that exists everywhere at once. If something happens here and something happens far away, we instinctively believe there is a fact of the matter about whether those two events occur at the same time. This belief is so deeply embedded in how we think that we rarely even question it. But Einstein did.
In special relativity, the assumption of a universal now does not survive, and the reason it fails is subtle. It comes from something we take for granted, the way we measure time at a distance. Imagine two lightning strikes hitting opposite ends of a long train.
They are moving toward one flash and away from the other. Because the speed of light is fixed, the light from the forward strike reaches them before the light from the rear. And here is the critical point. They are not allowed to say, "That's just because I'm moving." In relativity, the speed of light is the same in all inertial frames, so they must conclude something deeper. They must conclude that the events themselves were not simultaneous. Two observers, two valid frames of reference, two different answers to the question, did those events happen at the same time? This is not an illusion. This is not a delay in perception. It is a fundamental property of spacetime.
Simultaneity is not absolute. It depends on motion. And once that idea falls, everything else, time, length, even causality, must be reconsidered. There is no universal clock ticking for the universe. There is no single shared present. There is only space-time and how different observers move through it.
Time. Once simultaneity is no longer absolute, the next idea to fall is time itself. We tend to think of time as something universal, a steady flow, the same everywhere for everyone. A second here is a second there. A clock is a clock. But that assumption depended on something we have already lost, a shared definition of now. If observers cannot agree on what events are simultaneous, they cannot agree on how much time has passed between those events.
Time becomes tied to the observer. Now consider motion. If one observer moves relative to another, their measurements of time begin to diverge, not because their clocks are broken, but because time itself is not fixed. This is captured in a single expression.
T prime equals t divided by the square root of 1 minus v squared divided by c squared.
This is not a correction for perception. It is not an adjustment for signal delay. It is the relationship between time as measured in different frames of motion, As velocity increases, the denominator decreases, and the measured time expands. From one frame, a moving clock runs slow, but from that moving frame, it is everything else that runs slow. This is not a contradiction. It is a reflection of something deeper. Time is not a universal backdrop. It is part of the structure of spacetime, and it depends on how you move through it. There is no single clock for the universe. There are only clocks, each following its own path.
Length. If time is not universal, then space cannot remain untouched. We often think of length as something fixed, a solid property of an object. A meter is a meter, no matter how it moves. But this assumption quietly depends on time being the same for everyone. Once time begins to change with motion, space is forced to change with it. Otherwise, the speed of light could not remain constant. This leads to a surprising result. L equals L sub 0 times the square root of 1 minus v squared over c squared.
An object in motion is measured to be shorter along the direction of that motion, not because it is physically compressed in its own frame, but because space and time are intertwined. To measure length, we must define the positions of both ends at the same moment. But we have already seen that the same moment depends on the observer. So different observers, moving relative to the object, do not agree on where its ends are at the same time, and so they do not agree on its length.
This is not distortion in the ordinary sense. Nothing is being squeezed or crushed. Instead, it is the geometry of space-time revealing itself through motion. Length, like time, is not absolute. It depends on how you move. And together, time dilation and length contraction ensure that one thing remains unchanged: the speed of light.
Velocity. At this point, we have seen that both time and length depend on motion. That alone is enough to challenge our intuition. But now we arrive at something even more striking. Velocity itself does not behave the way we expect. In everyday experience, velocities simply add. If you walk forward on a moving train, your speed relative to the ground is just your walking speed plus the speed of the train. This seems obvious. It seems unavoidable. But this rule cannot hold if the speed of light is to remain constant. If velocities simply added, then chasing a beam of light would allow you to measure it moving more slowly. But this never happens. No matter how fast you move, light always moves at the same speed. So something must change. And that change is captured in this expression. U prime equals U plus V by 1 plus UV by c squared. Velocities combine in a way that prevents any object from exceeding the speed of light.
As speeds approach c, the denominator grows, and the result is forced to remain below that limit. This is not an arbitrary correction. It is the direct consequence of everything we have already seen. Time adjusts, length adjusts, and together they reshape how motion itself works. The familiar rules of addition are replaced by the geometry of space-time. No matter how velocities combine, the speed of light remains unchanged, and in preserving that one constant, our entire understanding of motion is transformed.
Rest.
Up to this point, we have seen that time changes with motion. Length changes with motion. Even the way velocities combine depends on motion. Now we arrive at the deeper implication. There is no absolute state of rest. In everyday thinking, it feels natural to believe that something, somewhere, must be truly at rest. A fixed background. A universal reference. Something against which all motion can be measured. But the structure we have uncovered does not allow this. In special relativity, every inertial observer is equally valid. There is no preferred frame, no hidden standard of rest. If you are moving at a constant velocity, you are fully justified in describing yourself as stationary and everything else as moving.
And the laws of physics will agree with you. This is not a limitation of measurement. It is a statement about reality. Motion is always relative. There is no experiment you can perform, no observation you can make that will reveal a state of absolute rest. The universe does not provide a fixed stage on which motion unfolds. Instead, motion exists only in relation to other motion. There is no absolute stillness, only relative movement, and the relationships between observers.
Space-time. By now we have seen that time changes with motion. Length changes with motion. Even the idea of simultaneity depends on how you move. At first, these effects seem disconnected, separate adjustments, corrections to different parts of reality. But they are not separate. They are all reflections of a deeper structure. Space and time are not independent. They form a single entity, space-time. This relationship is captured in a single expression. S squared equals c squared t squared minus x squared.
This quantity, s squared, is not like time alone, and not like distance alone. It is something more fundamental. And unlike time or length by themselves, this quantity remains the same for all observers. No matter how fast you move, no matter how you measure space or time, this space-time interval does not change. This is the key shift. What we once thought were separate, space and time, are actually intertwined aspects of a single geometry. When motion changes time, space must change with it. When space changes, time must adjust in response. They are bound together. And what remains constant is not time and not distance, but the structure that contains them both. Reality is not built from space and time separately. It is built from space-time.
Synchronization. If space and time form a single structure, then one of our most basic assumptions must also fail. The idea that clocks across space can be universally synchronized. In everyday life, we assume this is possible. We imagine a network of clocks all ticking together, agreeing on a shared now across distance. But this assumption depends on something we have already lost, a universal definition of simultaneity. To synchronize clocks, we must decide what events happen at the same time. We must compare distant moments and declare them equal. But in special relativity, that comparison is not absolute. because light takes time to travel, and because the speed of light is constant for all observers, any method of synchronization depends on motion. Two observers moving relative to each other do not construct the same synchronized network of clocks. They disagree on which distant events are simultaneous, and therefore they disagree on how clocks across space relate to each other. There is no single master clock for the universe, no global time standard embedded in reality itself. Each inertial frame builds its own consistent system of synchronized clocks, but those systems do not agree with one another. So synchronization becomes frame-dependent, not because our instruments are imperfect, but because the structure of space-time does not allow a universal now to be extended across distance. Clocks can be synchronized locally, but they cannot be synchronized universally.
Causality. At this stage, it may seem as though all structure has dissolved. Time depends on motion. Space depends on motion. Simultaneity depends on motion. Even synchronization depends on motion. It may feel as if nothing is fixed. But there is one boundary that does not break. Causality. In special relativity, cause and effect are preserved, but only within a strict limit. That limit is the speed of light. Events can influence other events only if there is enough time for light, or any signal travelling at or below light speed, to connect them. This creates a structure in spacetime called the light cone. Inside this structure, causes can reach their effects. Outside of it, they cannot. No signal, no influence, no interaction can cross that boundary. This means that while observers may disagree about the timing of distant events, they never disagree about what can affect what. Causality is preserved across all frames of reference. Even though simultaneity is relative, and even though time is not absolute, the ordering of cause and effect within the light cone remains intact. This is the deepest constraint imposed by the speed of light. Not everything is relative. Some relationships are protected by the structure of spacetime itself.
Physical processes. Up to this point, we have seen that time depends on motion. Space depends on motion. Even simultaneity and synchronization depend on motion. It may seem at first that everything becomes relative, that nothing remains fixed. But there is one structure that does not break. All physical processes follow a single invariant quantity. This quantity is called proper time. It is not the time measured by distant observers. It is not the time assigned through synchronization conventions. It is the time experienced along a physical path through spacetime, and it is given by tau is equal to the integral over time of the square root of 1 minus velocity squared divided by the speed of light squared. This expression is not describing perception. It is not describing how time appears. It is describing how time is accumulated. Every physical process, atomic decay, oscillations, biological aging, mechanical motion, evolves according to this quantity. Different paths through spacetime accumulate different amounts of proper time. A system moving at high speed accumulates less proper time than one at rest. A system deeper in a gravitational field accumulates less proper time than one farther away. But in every case, the rule is the same. The rate of physical change is governed by the geometry of spacetime itself,
not by observation, not by signal delay, not by perspective, but by the path taken through space-time. This is where relativity becomes physical. Time is not what we measure. Time is what is experienced along a trajectory.
Geometry of reality. At this point, all of the separate threads converge. Time was shown to depend on motion. Space was shown to depend on motion. Simultaneity, synchronization, and even velocity itself were revealed to be frame-dependent. Yet through all of this, one structure remained consistent. Not time, not space, not motion, but geometry. Final thought. The speed of light does not distort reality. It reveals that reality is not what we assumed. Reality is not what changes when you move. Reality is the rule that determines how everything changes when you move.